Welcome to the deep dive. Today we're plunging into, well, a truly fascinating realm. Cold and ultra-cold chemistry and physics. It's all sparked by this incredible collection of sources you've shared with us.
That's right.
Our mission really is to pull out the most mind-blowing insights and try to understand the downright strange ways matter behaves when we turn the cosmic thermostat way, way down.
Exactly. We're talking about slowing molecules down to what feels like a complete standstill. I mean, hovering near absolute zero.
Wow.
And it's at these crazy low temperatures that the fundamental forces, the ones running the microscopic world, they show us completely new sides, different interactions.
So new physics, almost.
In a way, yeah.
Yeah.
Get ready for some real head-scratching phenomena, and maybe a glimpse at potential applications that could genuinely change things down the line.
Okay, and look, don't sweat it if your physics knowledge peaked back in high school. We know you listening come from all sorts of backgrounds.
For sure.
And we're really committed to making this an engaging and, dare I say, fun exploration for everyone. Okay, let's unpack this.
Right. So where do we even begin? How do we define this ultra-cold realm? Well, a cornerstone interaction here is the van der Waals force.
The Van der Waals,
Right.
yeah.
Think of it like the weakest, most gentle kind of attraction between neutral particles.
Yeah.
And it gets stronger the closer they are. There's an equation, Vanderphi in high at a C6R66, but the key is it drops off fast with distance.
Okay, so it's like this super faint pull, almost like gravity, but way weaker. And it only really matters when particles are practically, bumping shoulders.
Pretty much.
Now, your sources also mention these characteristic scales, Van der Waals length, ABV, and energy. What are these telling us, like, in plain English?
Right. So essentially these equations, and don't worry about memorizing them, frac 12AC and frac 112 Eilers, they basically give us a natural ruler and an energy unit.
Okay.
Perfectly suited for these van der Waals interactions, these gentle hugs, let's say. The length tells you the typical distance where this hug really starts to become noticeable. And the energy, that's like telling us just how strong this hug is, on the energy scale that matters at these incredibly low temperatures. It just helps you get a feel for how these particles are going to behave.
Got it. So, characteristic distance, characteristic energy for this super weak attraction. Now, how cold do things actually have to get for us to enter this ultra-cold world?
Well, generally we say ultra-cold physics happens when the energy of the colliding particles, their kinetic energy, gas, becomes much, much smaller than this van der Waals energy scale.
Much smaller, like how much?
For a lot of common atom systems, this usually means temperatures dipping below 1 millikelvin. 1 millikelvin.
1,000th of a degree above absolute zero. That's just mind-bogglingly cold.
It really is.
So what's so special about these super low energies? Why do we care?
Here's where it gets really interesting. At these ridiculously low energies, right?
Yeah.
When particles barely have any zip to them, their interactions are mainly dictated by that long-range, super gentle tug of the van der Waals force, the 1367 part. And this allows the pure weirdness of quantum mechanics to just shine through. Suddenly, how these particles scatter, how they bounce off each other, it's governed by only a few partial waves.
Partial waves.
Yeah, think of them like very limited options for how they can approach and interact.
Yeah.
It's like they've lost all their fancy moves and only have a few basic ones left. Very quantum.
So as things slow down to a crawl, the quantum rules become much more obvious, much clearer. Now, this 1 mK rule, is that like a hard line in the sand, set in stone?
Not exactly, no. As your sources point out, this 1 mK mark isn't some universal law. It really depends on the specifics of the long-range interaction. Sometimes it's not just arc-count sevens.
Oh, okay.
And it depends on the unique characteristics of the system, the atoms or molecules involved. There are actually more general formulas for these length and energy scales that can handle different interaction types, like 1N2 for length and CN2 for length, and 1N2 for energy.
So the ultra-cold sign on the door is more of a guideline, depends on who's trying to get in. Your sources even have this table 1.1, showing these scales for different atomic pairings. What jumps out at you from that?
Well, what's truly striking is just the sheer variety. Take lithium colliding with lithium, Li. The length scale is around 47 $8, that's more radii, tiny distance units, and the energy scale is about 7.5 milK.
Okay.
Now compare that to cesium, CSEs, much larger length scale, over $108, but a drastically smaller energy scale, just 0.27 milK.
Wow, big difference.
Huge difference. And then you look at systems with ions, like lithium atom plus lithium ion, Li plus LEGO. The values are completely different again. It just shows how even adding a single charge totally changes the long-range game.
It's amazing how diverse these fundamental interactions can be, especially when you get this cold. Okay, moving on. Your sources really emphasize scattering experiments. They seem crucial for understanding these interactions. Why is scattering our main tool down there?
Think of it like this. Scattering experiments, where we carefully measure something called the cross-section.
The cross-section.
Yeah, it's basically the effective target size for collisions. How likely are they to hit each other? By measuring this cross-section, how it changes with energy, we get this energy-dependent map of the forces between the particles.
Ah,
So by firing these ultra-cold particles at each other and seeing how they bounce off or scatter, we can indirectly piece together the intricate details of the forces at play, the attractive parts, the repulsive parts.
it's like trying to figure out the shape of an invisible sculpture by throwing tiny marbles at it and seeing how they deflect.
That's a great analogy, yeah.
Yeah.
Exactly. We're probing the unseen by watching the outcomes of these incredibly gentle collisions.
Now, there's a general equation for this quantum scattering, involves something called the S matrix and phase shifts. Can you give us the basic idea without, getting lost in the math weeds?
Sure. At its heart, these equations like sigma for F2 boot plus 1, 1, LC2, 2, or the one with phase shifts, sigma for F2 plus 1, sin 2, they just tell us the probability of these ultra-cold particles scattering in different directions after they interact.
Okay, the probability.
Yeah. And the phase shift, delta in particular, think of it as a measure of how much the quantum wave of an incoming particle gets altered or kind of delayed as it feels the presence of the other particle.
Ah, so it's like a ripple effect on the wave.
Exactly. And that tiny shift in the wave tells us a whole lot about the interaction itself.
Okay, so these mathematical tools let us quantify how these particles scatter. Now, the Wigner threshold law sounds important for understanding what happens right when the collision energy gets as close to zero as possible. What's the key takeaway there?
The Wigner threshold law, it describes this really fundamental universal behavior. What happens to these collision probabilities as the particles almost come to a complete stop as their momentum colors goes to zero?
And what does happen?
What's fascinating is that for most types of bounces, what we call elastic scattering, where they just bounce off without changing internally, the likelihood of them happening actually drops to zero at these super low energies.
They just miss more often.
That's effectively, yes. Except, there's a crucial exception, swave scattering. This is when the particles are essentially colliding head-on with no sideways motion, no angular momentum, SWE bars.
Ah, the simplest kind of collision.
Exactly. This type of scattering doesn't vanish. It actually settles down to a constant value as the energy drops to practically nothing.
So right at the very edge of cold, it's all about these direct, head-on interactions. Everything else fades away.
Precisely. The law basically says a Limstedt era sigma, C12, C12, a constant related to something called the scattering length. It highlights that at these extreme energies, only swave scattering dominates, and that constant collision probability becomes a fundamental property, tied directly to the underlying interaction.
It's amazing how things simplify at such extremes. Just boils down to the head-on collisions.
Yeah.
Now, let's talk about control. This is exciting. Your sources mention Finow-Feshbach resonances as a really powerful tool. What are these, and how do they let us, tinker with these tiny interactions?
Right. Finow-Feshbach resonances, they're a truly quantum mechanical phenomenon, and they act like a master switch, almost, for how atoms and molecules interact.
A master switch? How?
Okay, so they happen when a scattering state that's just particles approaching each other, ready to collide, gets coupled, linked to a bound state in a different closed channel.
A closed channel, like a hidden pathway.
Sort of, yeah. Think of a closed channel as a hidden, usually energetically unfavorable state.
Yeah.
But it can suddenly become accessible if we give the system an external nudge. Usually that nudge comes from a magnetic field, sometimes an electric field.
So it's like we use an external field as a key to open up the secret passage between the collision state and a hidden bound state.
Precisely. And by very carefully tweaking the strength of this external field, maybe just by tiny amounts, we can fine-tune the energy difference between that initial scattering state and the hidden bound state.
And that does what?
This seemingly small adjustment can dramatically change the scattering length. And the scattering length is the crucial parameter that dictates the strength and even the type of interaction, attractive or repulsive. We can make them attract more strongly, less strongly, or even repel each other just by turning a knob on the magnetic field.
And this isn't just a tiny tweak to the interaction, right? Your sources mention a huge change observed in oxygen molecules colliding.
Oh, absolutely huge. In collisions between two specific oxygen molecules, OD2-2, at a staggeringly low 1 microkelvin.
Microkelvin, even colder.
Yeah, a millionth of a Kelvin. Scientists observe the elastic cross-section, the chance of them bouncing off each other changing by more than 2 orders of magnitude, a factor of over 100, just by tuning the magnetic field near one of these Feshbach resonances. That just shows you the incredible power these resonances give us to precisely control how these molecules behave.
That's like turning a dial and completely changing whether these molecules act like ghosts passing through each other or like they're covered in Velcro. Incredible. Now, the number of these resonances, how often you find them, seems to vary a lot between different atoms and molecules. Why is that?
Right, the density of these resonances, how many you typically find per unit of magnetic field, like per Gauss, it really depends on the unique internal characteristics of the atoms or molecules involved.
Makes sense.
So for simple alkali atoms like sodium or rubidium, you might find around, say, $10 of resonances per Gauss.
Right.
Quite sparse.
Okay.
For molecules like O222 interacting with O22, it's a bit denser, maybe 10 to 2 per Gauss, probably because their interactions are more intricate. They depend on orientation, things like that. But then you get to atoms with really strong magnetic properties like erbium or dysprosium. These are lanthanides. Their density of resonances can skyrocket to around 101 per Gauss.
10 per Gauss. Why so many?
It comes down to the complexity of their interactions. The anisotropy, meaning it depends strongly on direction, and the strength of their internal magnetic moments, their magnetic handles, basically.
So it sounds like the more internal knobs and levers a particle has, the more ways we can potentially find these resonances and influence its interactions using external fields. Fascinating. Okay, let's switch gears a bit and talk about Bose-Einstein condensates, or BECs. We hear about them all the time in the context of ultra-cold physics. What are they, in simple terms?
Right, BECs. So imagine you take a whole bunch of identical particles called bosons. These are particles with a specific type of quantum spin, like photons or certain atoms like rubidium-87, and you cool them down to unbelievably low temperatures.
Colder than we've already been talking about.
Often, yes, down into the nanokelvin range sometimes. At that point, something amazing happens. A large fraction of these bosons suddenly decide to all occupy the exact same lowest possible quantum energy state.
All of them in the same state.
A huge chunk of them, yeah. They essentially lose their individual identities and start acting as one single giant quantum wave. That collective state is the Bose-Einstein condensate.
So instead of a chaotic swarm of individual particles bouncing around, they all become perfectly synchronized, like a quantum choir singing the same note.
That's a great way to put it, exactly. And their collective behavior is often described by a really powerful equation called the Gross-Pitaevsky equation.
Ah, yes. The sources mention that for Ablaevely plus U5. Looks intense.
It does, but the components make sense. It looks a bit like the normal Schrödinger equation, but it has an extra term, the U$$ tart. That term accounts for the interactions between the bosons in the condensate. U$ is related to that swave scattering length we talked about.
Okay, so it describes how the giant wave moves, considering the trap, and how the particles within the wave interact. U$?
Precisely. It tells us how this giant quantum wave evolves in space and time. Your sources also point out an interesting connection. It has similarities to how a Rydberg electron behaves in a dense medium. Just shows how these concepts can link up across different areas of physics.
Interesting side note. Now, the Gross-Pitaevsky equation seems complex. Is there a simpler way to think about the shape of a BEC? The sources mention the Thomas Fermi approximation.
Yes, the Thomas Fermi approximation. It's a useful simplification, especially when the interactions between the particles in the BEC are strong, and there are many particles. It basically says that the kinetic energy part of the Gross-Pitaevsky equation, the Nobel-Tufad term, becomes less important compared to the interaction and trap terms.
And what does that lead to?
It leads to a very simple picture. The density profile of the BEC essentially mirrors the shape of the external trap holding it, but inverted. The density URL is roughly proportional to BA.
So if you have a BEC in, say, a spherical bowl-shaped trap, like a harmonic trap where frac 1 mega to under mega 2, 2-2.
Then the Thomas Fermi approximation predicts that the density of the BEC will also have a shape related to that bowl, specifically an inverted parabola. Looks like the omega-2 U2 you do along omotadinals, higher density in the middle, falling off towards the edges.
So the container really dictates the form of this quantum blob, almost like jelly in a mold. That's surprisingly intuitive.
It is, yeah. It's a very useful picture for large condensates.
Okay, and one last concept for BECs here, the healing length, 2 L's. What does that tell us?
The healing length, it's a fundamental length scale within the BEC. Think of it as the minimum distance over which the BEC's wave function can significantly change or bend.
Bend, like if you poke it.
Exactly. If you introduce some kind of local disturbance like a defect or just the edge of the trap, the healing length tells you the distance over which the BEC wave function can heal or smooth itself out and recover back to its bulk density. It's defined by balancing the kinetic energy and interaction energy. Ration.
So a short healing length means the BEC is very stiff, very good at smoothing out any wrinkles quickly.
Right. And a longer healing length means it's sort of more floppy, takes longer to adjust to changes. It depends on the density and the interaction strength.
Got it. Okay, let's move on to another type of interaction. Dipole interactions. How are these different from the van der Waals forces we started with?
Good question. While van der Waals forces between neutral atoms are generally attractive at long distances and isotropic, meaning the same in all directions, dipole interactions are quite different.
How so?
Firstly, they fall off less rapidly with distance, typically is 133 instead of Earth's with 66. And secondly, they are inherently anisotropic.
Anisotropic, meaning direction matters.
Absolutely. The force can be attractive or repulsive.
Yeah.
And it depends strongly on how the dipoles, whether they're electric or magnetic, are oriented relative to each other and relative to the line connecting them.
Okay, so much more complex than the simple van der Waals hug.
Definitely. The general equation, 1's B phi Fe, minus B3, math BFE, math BFE, math BFE, math BFE, math BFE, math B, math BFE, really shows this intricate dependence on the orientations, math BFE ideal, and the separation vector, math BR.
Right. And the overall strength is set by this constant CDD. What determines how big that is?
CDDs depends on whether we're dealing with magnetic dipoles or electric dipoles. For magnetic dipoles, like those from electron spin, CDD is related to the magnetic moments and the vacuum permeability, money $2. Typical magnetic moments are on the order of the Bohr magneton, a fundamental constant.
Okay.
For electric dipoles, which you get in polar molecules, CDD depends on the electric dipole moments, dealers dollars, and the vacuum permittivity epsilon dollar. Electric dipole interactions are generally much stronger than magnetic ones.
So, the inherent magnetic or electric personality of the particles dictates how strongly they interact through this directional force. Now, how do these dipolar forces change the behavior of BECs if the particles have these dipoles?
Well, if you make a BEC out of particles with significant dipole moments like chromium atoms or certain polar molecules, then the Gross-Pityevsky equation needs another term added to account for these long-range anisotropic dipolar interactions.
Makes sense.
The equation gets even more complicated. Frank U5 plus V5 plus UD3 spar, that integral term represents the average dipolar interaction felt by a particle from all the others in the condensate.
And what does this extra term do to the BEC?
It can have dramatic effects. Because the interaction is anisotropic, it can cause the VEC to deform, maybe become elongated or flattened depending on the trap geometry and how the dipoles are aligned. It can also lead to new kinds of collective excitations and even instabilities where the condensate can collapse under certain conditions if the dipolar attraction becomes too strong relative to the repulsion from the contact interaction. Either dollars alls.
So these directional forces can lead to more complex shapes and potentially more fragile BEC structures.
Very interesting. Okay, now, actually getting molecules down to these ultra-cold temperatures and trapping them. That seems like a huge technological challenge, right? Especially given they have all this internal structure, rotations, vibrations.
You're absolutely right. Cooling and trapping molecules is a much, much bigger hurdle than it is for atoms. Atoms are simpler. Molecules have all these internal energy levels, which makes standard laser cooling techniques, for example, much harder to apply.
So how do scientists tackle it? What are some of the key methods?
Well, there's a whole toolbox they've developed. A common starting point is often using supersonic jets. Supersonic jets? Like for airplanes?
Sort of, but on a much smaller scale. You expand a gas mixture through a tiny nozzle into a vacuum. This expansion process cools the molecules significantly, down to maybe a few Kelvin, and it creates a beam where the molecules are mostly moving in the same direction with a fairly narrow velocity spread. It also tends to cool their internal rotational and vibrational states somewhat.
Okay, so it's like creating a relatively cold, well-behaved stream of molecules to start with. What happens next to get them even colder?
From there, several techniques can be used. One is optical Stark deceleration.
Optical Stark deceleration? Sounds fancy.
It is pretty clever. It uses pulses of laser light, but not to directly absorb and emit photons like in laser cooling. Instead, it uses the AC Stark shift, the way a molecule's energy levels shift in the presence of the laser's electric field. By switching the laser on and off at precisely the right times as molecules pass through the beam, you can selectively slow down bunches of molecules. It's like applying a timed optical brake.
A molecular brake based on light shifts. Cool. What else?
Then there is laser cooling of molecules. But it's tricky. You need to find molecules that have very specific energy level structures, almost like atoms, allowing for a nearly closed cycle of laser excitation and spontaneous emission.
A closed cycle, meaning they keep returning to the state you started from.
Exactly. So they can scatter many, many photons, which is what provides the cooling force. But because molecules vibrate and rotate, they can easily leak out of the cycle into other states. So you often need additional repumping lasers to push them back into the main cooling cycle. The LF molecule is one example where this has been successfully demonstrated.
Sounds incredibly precise and very molecule-specific. What about methods that don't rely so directly on lasers hitting specific transitions?
Buffer gas cooling is a really important one. Here, you inject the molecules you want to cool into a cryogenic chamber filled with a cold, inert buffer gas, usually helium-3 or helium-4, cooled down to maybe below 1 Kelvin.
And the helium cools the molecules.
Right. The molecules collide with much colder helium atoms. Through many elastic collisions, the molecules lose their kinetic energy and thermalize with the buffer gas. They eventually reach a temperature close to that of the helium.
How efficient is that?
The efficiency depends on the mass ratio between the molecule and the buffer gas atom. It's described by this factor, kappa, plus m plus Bickler-Mahler, where molecule is the hot molecule mass and molecule is the buffer gas mass. The temperature difference decreases exponentially with the number of collisions, not in kappa. So lighter buffer gases and more collisions are better.
So it's a more general collisional way to bring the temperature down, relying on thermal contact. Okay, so we've cooled them. What about holding on to these ultra-cold molecules? Trapping them.
Trapping is crucial, of course. One major technique is optical trapping, often using optical dipole traps. This uses the force exerted on the molecules by an off-resonant laser beam.
Off-resonant, so the laser frequency isn't tuned to hit an actual transition.
Correct. The laser frequency is detuned, usually quite far from any molecular resonance. The molecule still feels a force because the laser light induces an oscillating dipole moment in it. The strength of this dipole potential, UD-Ja, depends on the laser intensity, the dipole star, and the detuning delta.
And how does that create a trap?
Well, if the laser is red detuned, meaning its frequency is below a molecular resonance, the potential is attractive towards regions of high laser intensity. So a focused laser beam can create a trap right at its brightest spot.
Okay.
If the laser is blue detuned frequency above resonance, the potential is repulsive from high intensity. So you can use, say, hollow laser beams, like donut-shaped Laguerre Gaussian beams, to trap molecules in the dark central region. You also have to worry about photon scattering, gamma, which can heat the molecules, so you generally want large detuning and moderate intensity.
So we're using these carefully shaped light hands to hold the molecules. Are there other kinds of hands?
Yes, magnetic trapping is another key technique, but it only works for molecules that have a magnetic moment, paramagnetic species. Those with unpaired electron spins, like oxygen or OH radicals.
How does that work?
It relies on the interaction between the molecule's magnetic moment and an external, spatially varying magnetic field. If you design the magnetic field correctly, you can create a point of minimum magnetic field strength in free space. Molecules that are low field seeking, meaning their energy decreases as the field strength decreases, will be attracted to this minimum and trapped there.
A magnetic valley they roll into.
Exactly. Though there's a catch, a fundamental theorem called Earnshaw's theorem says you can't create a static magnetic field maximum in free space, only a minimum. So you can only trap low field seekers this way.
Interesting limitation. Now, the final trick often used to reach the very lowest temperatures, even in these traps, is evaporative cooling. How does that work for molecules? We heard about it for atoms.
It works essentially the same way for molecules, and it's often the crucial last step to reach quantum degeneracy, like BEC. The basic idea is straightforward. You selectively remove the most energetic, hottest molecules from your trap sample.
How do you do that? Just open the trap slightly?
Sort of. You gradually lower the depth of the trap potential, maybe by reducing the laser power in an optical trap or adjusting the magnetic fields. This allows the fastest moving molecules, the ones with enough energy, to climb highest in the potential, well, to escape over the lowered edge.
Okay, so the hot ones leave.
Right. The remaining molecules then rethermalize through collisions amongst themselves. Since the average energy per particle has decreased, because the hot ones left, The overall temperature of the remaining sample drops. You repeat this process, continuously lowering the trap depth and letting the hottest ones evaporate.
And the remaining ones get colder and colder.
Exactly. For this to be efficient, you need the trap to be deep enough initially compared to the temperature, characterized by this parameter DLS-UTRAC-KB-T2. You typically want θ to be greater than 5, maybe even 10, so you don't lose too many of the colder molecules accidentally while letting the hot ones go.
So it's like the coldest members of the group get even colder because the most energetic ones volunteer to leave.
Clever. Okay, let's delve into the actual collisions between these ultra-cold molecules now. Your sources point out they're much more complex than collisions between simple atoms. Why is that?
The added complexity comes directly from the fact that molecules aren't just structureless points. They have internal degrees of freedom. They can rotate, they can vibrate, their electrons can be in different energy states, electronic states, and then there are even finer details like spin interactions within the molecule, fine structure, and interactions with nuclear spins, hyperfine structure.
So many moving parts inside each molecule. Exactly. All of these internal degrees of freedom can change during a collision. Energy can be exchanged between the motion of the molecules towards each other, kinetic energy, and these internal motions. This makes the whole interaction landscape much, much richer and, frankly, harder to predict than simple atom-atom collisions. The Hamiltonian, the quantum operator, describing the system's energy gets way more complicated, including terms for all these internal motions and their couplings.
So many more ways for molecules to interact, exchange energy, change their internal state during a collision. What happens if the colliding molecules are identical? Does that quantum indistinguishability we touched on earlier come back into play?
Absolutely. It's crucial. When you have identical molecules colliding, say, two identical oxygen molecules, quantum mechanics demands that the total wave function describing the collision must have a specific symmetry when you mathematically swap the two molecules.
Symmetric or antisymmetric, right?
Right.
Depending on boson or fermion.
Precisely. If the molecules are bosons, like 2-port O2, the total wave function must be symmetric under exchange. If they're fermions, like 17O2 detour due to its nuclear spin, it must be antisymmetric. This symmetry requirement profoundly affects which quantum states are allowed for the colliding pair and directly modifies the scattering outcomes. You get interference effects between different scattering pathways that you just don't see with distinguishable particles. The cross-section equation actually gets an extra interference term, sigma-ant, because of this.
So the fact that we fundamentally can't tell them apart at the quantum level has real, observable consequences for how likely they are to bounce off each other in certain ways.
Wow. Now, what happens when these collisions occur in the presence of an external field, like the magnetic fields used for trapping or Feshbach resonances?
External fields add another layer of complexity, but also control. They break the perfect spherical symmetry that you'd have in free space. This means that the total angular momentum of the colliding pair isn't necessarily conserved in the same way anymore.
So the rules change. The relevant quantum numbers change. Instead of focusing on the total angular momentum, the projection of the angular momentum onto the axis defined by the external field becomes the crucial quantity. Collisions can now change this projection. The likelihood of scattering into different final states will depend on these initial and final projection quantum numbers and how they couple to the field and the interaction potential. The cross-section formula gets modified to reflect this dependence on the field direction.
So the external field imposes a kind of directionality onto the collision, influencing the outcome based on how the molecules align or change their alignment with respect to that field. Your sources use the specific example of ultra-cold collisions of oxygen molecules, O2 or 2, in a magnetic field. What makes this system particularly interesting to study?
Oxygen, O2 or 2, is interesting for several reasons. It's a molecule, so it has rotational structure. It's also paramagnetic in its ground electronic state. $3 sigma, meaning electron spin and thus a magnetic moment, which allows it to be magnetically trapped and manipulated with Feshbach resonances.
Connects back to earlier points.
Exactly. Furthermore, oxygen exhibits what's called spin-rotation coupling. The molecule's physical rotation is linked to the orientation of its electron spin. And in the 17 isotope, you also have nuclear spin, it's a fermion, leading to hyperfine structure. All these spins and rotations interacting in a magnetic field lead to a complex pattern of energy levels, which are described in part by equations like 5.61 and 5.62 in your sources. Studying collisions probes all this rich internal structure.
And these internal state changes during collisions can have practical consequences in experiments, right? Your sources mention spin relaxation leading to trap loss. How does that happen?
Yes, that's a major issue. Spin relaxation occurs when a collision causes a molecule to change its spin state, specifically its orientation relative to the magnetic trapping field. Remember, magnetic traps only hold molecules in certain spin states, low field seekers.
Right.
If a collision flips the spin into a high field seeking state or just a state that isn't trapped, the molecule feels a repulsive force from the trap center and is ejected. It's lost from the sample.
What causes the spin flip during the collision?
It's driven primarily by interactions between the two colliding molecules. Things like the magnetic dipole interaction between their electron spins, and also the fact that the main van der Waals interaction itself depends slightly on the relative orientation of the molecules, potential energy surface anisotropy. These interactions can couple different spin states together, allowing transitions during the collision.
So these subtle interactions during the brief encounter can have a big impact on whether we can actually hold on to the molecules long enough to study them. Finally, in this section, the discussion touches on the theoretical tools needed to actually predict the outcomes of these complex molecular collisions. What are the main approaches? It sounds hard.
It is computationally very demanding, yes.
Mm.
The gold standard approach is to solve what are called quantum mechanical coupled channel equations.
Coupled.
Yeah. You essentially write down the Schrödinger equation for the entire colliding system, including terms for the relative motion of the molecules and all their relevant internal states, rotational spin, etc., and the interactions coupling them. This results in a large set of coupled differential equations, one equation or channel, for each possible internal state configuration.
That sounds like a lot of equations.
It often is. Hundreds or even thousands of coupled equations are not uncommon for realistic molecular collisions. You usually can't solve these analytically, so you rely on sophisticated numerical algorithms, like the Numerov propagator mentioned in the sources, to integrate these equations step by step and calculate the probabilities for scattering into different final states, getting the cross sections.
So it requires serious computing power to accurately simulate these molecular encounters from first principles. Okay, let's shift focus slightly now to three-body collisions. We've mostly talked about two particles bumping into each other. Why do three-body collisions become important in the ultracold regime?
Three-body collisions, where three particles all interact with each other simultaneously or nearly simultaneously, become increasingly relevant as the density of the ultracold gas increases. While two-body collisions are always the most frequent, the rate of three-body collisions scales much faster with density, as density cubed versus density squared for two-body.
So in the dense samples we often create, like BECs, they start to happen more often.
Exactly. And they can be very important. Three-body processes are often the main pathway for chemical reactions to occur in ultracold gases, where you might need three atoms to come together for one to carry away excess energy, allowing the other two to form a stable molecule. They are also fundamental to understanding the stability of BECs, three-body loss, and exploring exotic few-body physics.
Now, the concept of universality comes up again here, often linked to something called the renormalization group approach. What's the basic idea behind this universality in the context of three-body collisions?
Universality in ultracold collisions is this really beautiful, powerful idea. It suggests that at sufficiently low energies, the behavior of systems involving three or even more interacting particles can become remarkably independent of the specific, messy details of how those particles interact at very short distances.
So the short-range stuff doesn't matter as much.
Right. Their behavior becomes governed primarily by just a few key parameters, like the two-body scattering length we've already discussed. It implies that very different microscopic systems might exhibit the same macroscopic three-body physics if their scattering lengths are similar. The renormalization group is a mathematical framework that helps us understand why and when this happens, how the physics changes as we look at different energy scales, and how these universal behaviors emerge as fixed points in the theory.
So despite all the microscopic differences between, say, different types of atoms, their collective three-body behavior at ultracold temperatures can become surprisingly alike, governed by just one or two numbers. That's pretty profound. Your sources also mention effective field theory, EFT, as another tool here. How does that fit in?
Effective field theory is another powerful theoretical framework that kind of embraces this idea of universality. EFT provides a systematic way to build theories that are valid only within a specific energy range, in this case ultracold energies, but focusing only on the relevant degrees of freedom and interactions for that energy scale.
So it simplifies things by ignoring the high-energy details.
Exactly. You don't need to know the full, complicated interaction potential. Instead, you represent the interactions using a few coupling constants related to things like the scattering length that capture the essential low-energy physics. In the context of three-body problems, EFT often involves introducing auxiliary fields, like a dimer field that represents a temporarily bound pair of particles, which can help organize the calculation of three-body processes.
And what about the Skorniakov to Martirosyan STM integral equation? Sounds specific. What does that help us understand?
The STM equation is a specific landmark integral equation developed back in the 1950s. It was designed to describe the quantum scattering of three identical bosons interacting via short-range forces, specifically addressing the problem of a neutron scattering off a deuteron, the proton-neutron-bound pair.
So a foundational tool for three-body scattering.
Yes, very foundational. It essentially sums up all the possible sequences of two-body interactions that can happen among the three particles. However, it famously ran into mathematical difficulties. It produced infinities, divergences, which hinted that something crucial was missing in the physics assumptions of the time.
What was missing?
It turned out that resolving these issues required introducing a new physical parameter, a three-body parameter, essentially acknowledging that you can't always predict three-body behavior just from two-body interactions alone, especially when the scattering length is large. This whole issue connects deeply to the need for renormalization in these theories.
And finally, in this realm of three-body physics, the truly intriguing Efimov states are mentioned. Can you give us just a quick glimpse into what these are all about? They sound exotic.
Oh, they are exotic. Efimov states are a genuinely counterintuitive quantum mechanical phenomenon predicted by Vitaly Efimov in the 1970s. He showed that under certain conditions specifically, when the two-body scattering length between particles is very large compared to the range of the interaction, three identical bosons can form an infinite series of bound states.
An infinite series, bound states. But wait.
Here's the kicker. These states can exist even if no two of the particles are strongly enough attracted to form a stable bound pair by themselves.
What? How is that even possible? Bound states forming from particles that can't even stick together in pairs.
It's purely a quantum mechanical effect, tied to the long-range nature of the effective interaction in this resonant regime. The potential behaves in a peculiar 1r2 way at long distances in hyperspherical coordinates, a way of describing three bodies, which allows for this infinite geometric ladder of states. Their sizes scale universally, each state being about 22.7 times larger than the next deeper one for identical bosons.
That sounds absolutely wild. A purely three-body binding mechanism. Incredible. Okay, let's switch gears again, quite dramatically perhaps, and explore the world of Rydberg physics at ultra-cold temperatures. First off, what are Rydberg atoms, and what makes them so special?
Rydberg atoms are atoms where one electron has been kicked up into a very high energy level, one with a large principal quantum number. Think n out of $3, even 100 or more, compared to n or ho for ground state atoms.
So the electron is really far out.
Extremely far out. This makes Rydberg atoms physically enormous. Their size scales roughly is 722. They also have very weak binding energies for that outer electron. Scaling is other than 22, making them incredibly sensitive to external electric and magnetic fields. And they tend to have very long lifetimes compared to atoms in lower excited states. Scaling is 723.
So they're like these giant, fragile, super sensitive, long-lived versions of ordinary atoms. Very different beasts. Now, your sources discuss ultra-long-range Rydberg molecules. What on earth are those?
These are truly bizarre molecules. They're formed not by the usual chemical bonds, but by the interaction between a single Rydberg atom and one or more ground state atoms that happen to be located within the vast orbit of that highly excited Rydberg electron.
Effectively, yes. The Rydberg electron is so far out and moving relatively slowly that a ground state atom can wander into its path. The interaction that binds them is actually a very low-energy scattering interaction between the nearly free Rydberg electron and the neutral ground state atom. So the electron acts like the glue.
In a very quantum mechanical way, yes. It's a realization of some early ideas by Enrico Fermi back in the 1930s about how Rydberg states might be perturbed by a background gas, but now observed and controlled in ultracold experiments. Examples include molecules with wonderful names like trilobite molecules and butterfly molecules.
Trilobite and butterfly molecules. The names alone paint a picture of something really strange and wonderful. Why those names?
The names come from the calculated shape of the Rydberg electron's probability density in these molecular states. In trilobite states, the electron density looks remarkably like the fossilized shape of a trilobite, strongly peaked around the location of the ground state atom due to the electron-atom scattering. Butterfly states have a more complex nodal structure resembling butterfly wings.
Amazing. And the potential energy curves for these Rydberg ground state interactions are described as oscillatory. Why do they have this up and down wiggly behavior?
Ah, the wiggles. Those oscillations in the potential energy as you change the distance between the Rydberg core and the ground state atom are a direct reflection of the wave-like nature of the Rydberg electron itself.
How so?
The Rydberg electron's wave function has nodes and antinodes places where the probability of finding it is high or low that oscillate as you move away from the atomic core. The energy of the interaction with the ground state atom depends on the electron density at the location of that ground state atom. So as you move the ground state atom further out, it samples different parts of the electron's oscillating wave function, leading to oscillations in the binding energy.
It's like the ground state atom is surfing the quantum waves of the Rydberg electron, feeling the crests and troughs.
That's a perfect way to visualize it, yeah.
Yeah.
It's directly probing the structure of the Rydberg wave function.
So cool. Finally, in this Rydberg section, Rydberg neutral, inelastic, and reactive collisions are mentioned. What kinds of things can happen when these giant Rydberg atoms actually bump into other normal ground state atoms? It's not just forming molecules.
No, other processes can definitely happen, especially if the collision energy is a bit higher. One outcome is L-mixing. The collision can change the orbital angular momentum state, the Gaulter quantum number, of the Rydberg electron, often mixing states with high dollars, more circular orbits, into states with low elliptical orbits that penetrate closer to the core.
Okay, changing the shape of the orbit. What else?
Then there's chemionization. The collision can cause the Rydberg atom to lose its electron altogether. This can happen through penning ionization, where the Rydberg atom transfers its excitation energy to the ground state atom, ionizing the partner, all plus A right all A plus A plus E dollar. Or it can happen via associative ionization, where the two atoms actually stick together to form a molecular ion, releasing the electron, all plus A right RO A2 plus eta.
So these gentle encounters with giant atoms can actually strip electrons away or even forge new chemical bonds, forming ions. Fascinating range of possibilities. Okay, let's move on now to hybrid atom-ion systems. What defines such a system in the world of ultracold physics? Sounds like mixing and matching.
That's exactly what it is. Hybrid systems, in this context, usually refer to experiments where you combine two distinct quantum systems that are trapped and interacting. Specifically, it often means having cold or ultracold neutral atoms co-trapped and interacting with cold ions.
Atoms and ions together in the cold. Why do that?
It opens up a whole new playground. You can study fundamental interactions between charged and neutral particles at very low energies, where quantum effects dominate. Ions offer strong, long-range interactions, 100R44 potential with induced dipoles in atoms, and can be trapped very tightly. You can potentially use the ion to probe the neutral cloud, or use the atoms to cool the ion, or even control chemical reactions between them at an unprecedented level.
How are the ions typically held in place in these hybrid setups? We mentioned magnetic traps for some atoms molecules, optical traps. What about ions?
The workhorse for trapping ions is the Paul trap, or RF trap.
Yeah.
These use a combination of rapidly oscillating radio frequency electric fields and static DC electric fields.
Oscillating fields, how does that trap anything?
It's quite ingenious. The oscillating field creates what's called a pseudo-potential. Averaged over time, the ion feels an effective potential that pushes it towards the center of the trap, where the RF field is weakest. It's a dynamic confinement.
So it's constantly being pushed back towards the middle by the wiggling field.
That's the essence of it. However, a consequence is that the ion isn't perfectly still at the trap center. It always has some residual driven motion from the RF field, called micromotion. This can be a source of heating in atom-ion collision experiments if it's not carefully managed.
So the ion is held, but it has its own little quantum dance or jiggle that you have to account for. Now, when we have these ions and neutral atoms interacting, how do we even begin to describe their collisions? What's the simplest picture?
At cold temperatures, the simplest classical picture for reactive ion-neutral collisions is often the Langevin model.
Langevin model, what's the idea?
It's based purely on the long-range attraction between the ion's charge and the dipole moment it induces in the neutral atom. This interaction potential goes like 100R44. The Langevin model calculates the maximum impact parameter, the sideways distance for which this attraction is strong enough to capture the atom, pulling it into a collision trajectory that spirals inwards.
So if the atom gets close enough sideways, it's guaranteed to spiral in.
Basically, yes. The model assumes that if the atom gets captured in this way, gets within a critical distance Dahl's collars, a reaction occurs with 100% probability. It leads to a remarkably simple prediction for the reaction rate constant. 2-Pelbine and alpha, where alpha is the polarizability of the neutral atom, and 2-Bri is the reduced mass.
And the striking thing is,
It's independent of the collision energy. The rate just depends on the fundamental properties of the atom and ion, not how fast they're initially moving towards each other, at least in this simple classical picture, at low energies.
that's a really powerful baseline prediction. What about when they don't react, just bounce off each other? Elastic collisions?
Right, elastic atom-ion collisions are also important. Quantum mechanically, these are described, like other collisions, by calculating scattering phase shifts based on the full interaction potential, including the short-range part, not just the 144. The cross-section sigma L will generally depend on energy. Other interesting processes mentioned in your sources include radiative charge transfer, where the electron hops from the atom to the ion, or vice versa, and a photon is emitted, and radiative association, where the atom and ion collide and stick together to form a molecular ion, again stabilized by emitting a photon.
So light emission can play a crucial role in stabilizing the outcomes of these atom-ion encounters, either forming new ions or new molecules. Okay, let's broaden the scope slightly to few body processes involving ions and neutrals. What makes dealing with, say, 3 or more particles, where at least one is an ion, so much harder to understand than the two-body case?
Well, as soon as you go beyond two bodies, the complexity just explodes, whether they're all neutral or involve ions. The number of interactions, the possible arrangements, the ways energy and momentum can be exchanged, it all becomes vastly more complicated.
More moving parts, harder math.
Definitely harder math. Describing the motion requires more coordinates. We often use specialized coordinate systems like Jacobi coordinates, which help separate the center of mass motion from the relative motions within the system. Another powerful approach, especially for identical particles or highly symmetric systems, is using hyperspherical coordinates, which treat all the particles on a more equal footing.
These are just mathematical tools to try and tame the complexity.
Exactly. They provide different perspectives that can make the problem more tractable, but it's still fundamentally a very challenging theoretical problem, the quantum few-body problem.
And what kinds of specific processes are we particularly interested in when we have a few ions and neutrals interacting together?
One really important process, analogous to the neutral case, is three-body recombination involving an ion. For instance, an ion, 1 plus dollar, colliding with two neutral atoms, dollar, could lead to the formation of a molecular ion, AB plus dollar, with the third atom, dollar, carrying away the excess energy, A plus B, right arrow, AB plus B.
So forming molecular ions this way.
Right. Understanding the rates and mechanisms of these recombination processes is crucial for predicting the chemistry and lifetimes of cold plasmas or ion-atom mixtures. To tackle this theoretically, concepts like opacity functions are sometimes used.
Opacity functions?
Yeah, they basically represent the probability of a reaction, like recombination, occurring as a function of the initial conditions, like the impact parameters and energy. It's a way to encode the outcome of the complex close-range interaction within a simpler framework.
So it's like mapping out the likelihood of this delicate three-particle dance resulting in a lasting bond. Okay, finally, let's focus specifically on cold chemical reactions between molecular ions and neutral atoms. What new wrinkles are introduced when one of the charged reactants is itself a molecule, with its own internal vibrations and rotations?
Having a molecular ion reactant adds a whole new dimension, literally. Now, the internal state of the molecule, its specific vibrational level and rotational level, GR, can play a critical role in the reaction dynamics.
How so?
Well, the energy stored in these internal states can potentially fuel the reaction or influence which reaction pathways are open. Also, the orientation of the molecular ion relative to the incoming atom might matter. We can now ask questions like, does vibrating the molecular ion make it react faster? Does the reaction produce molecules in specific vibrational or rotational states? It offers a much richer landscape for controlling chemistry.
And how are these complex reactions typically studied in the ultra-cold lab or on the computer?
Experimentally, it's challenging, but involves preparing molecular ions in specific quantum states and reacting them with cold atoms. Theoretically, a very common tool is the quasi-classical trajectory, PCT method.
Quasi-classical, so not fully quantum.
Right. QCT bridges classical and quantum mechanics. You run classical trajectories from the nuclei moving on a potential energy surface that's usually calculated using quantum chemistry methods. But, and this is the quasi part, the initial conditions for the trajectories, like the vibrational energy and phase of the molecular ion, are chosen to mimic the quantum state you're interested in.
So you run many classical simulations with quantum starting points.
Exactly. You run thousands, maybe millions of these trajectories with slightly different starting conditions sampled from the initial quantum distribution. Then you analyze the outcomes. Statistically, did a reaction happen? What products were formed? What states are they in? This gives you estimates for reaction probabilities, cross-sections, and product distributions.
And what are some of the typical outcomes you might see when a molecular ion hits a neutral atom at these low energies?
Several things can happen. You might just get elastic scattering where they bounce off, or you could get inelastic scattering where the internal state changes. A common inelastic process is vibrational quenching.
Vibrational quenching.
Yeah, where the molecular ion starts in an excited vibrational state and collides with the atom, ending up in a lower vibrational state. The lost vibrational energy gets converted into kinetic energy of the products, pushing them apart faster.
So the collision calms down the molecule's vibration.
Right. Or you can have actual reactive processes. For example, substitution reactions, where the atom replaces one of the atoms in the molecular ion, or even dissociation, where the collision is energetic enough to break the molecular ion apart. Different binning methods, like uniform or Gaussian binning, are used in QCT to assign the final classical states back to quantum vibrational levels.
Your sources introduce this adiabaticity parameter when discussing vibrational quenching. What does that tell us about how efficiently vibrational energy gets transferred during the collision?
The adiabaticity parameter, TOC-TAV, is a really useful concept. It compares the characteristic timescale of the collision itself, roughly how long the particles are strongly interacting, with the internal timescale of the molecule's motion, like its vibrational period.
Okay, collision time versus vibration time.
Exactly. If your TOC-TAV is large, collision is slow compared to vibration, the process tends to be adiabatic. This means the molecule's vibration can adjust smoothly to the presence of the approaching atom without easily changing its quantum state. Energy transfer is inefficient.
It just adapts.
Right. But if TEFITS is small, collision is fast compared to vibration. The interaction is sudden, non-adiabatic. The molecule's vibration doesn't have time to adjust, making it much easier to transfer energy and change the vibrational state. Quenching becomes more efficient.
That makes intuitive sense. A sudden jolt is more likely to disrupt the internal motion than a slow approach. Now, your sources also mention statistical capture models for this vibrational quenching. What's the underlying idea there? Seems different from QCT.
It's a different perspective, often useful at very low collision energies. These models typically assume a two-step process. First, there's long-range capture, governed by that 124 Eulers-induced dipole potential, just like in the Langevin model. If capture occurs, the atom and molecular ion are drawn together. Okay, step 1, get caught. Step 2, form a collision complex. It's assumed that once they're close, they form a temporary, relatively long-lived three-body complex. Within this complex, the energy, initial collision energy plus internal energy, gets rapidly scrambled and redistributed among all the available ways the energy can be stored: vibration, rotation, relative motion, essentially in a statistical, almost random way.
Like shaking up a bag of energy modes.
Kinda, yeah. The probability of ending up in a specific final state, like a lower vibrational state, is then assumed to be proportional to the density of available states for that outcome, subject to energy and angular momentum conservation. It predicts that quenching rates might approach the initial capture rate if the complex lives long enough.
So a two-stage process. Long-range attraction, followed by a chaotic reshuffling of energy in this temporary partnership. Your sources present some results from QCT studies of collisions between barium-rubidium ions, $, and neutral rubidium atoms, Rb. What were some of the key findings?
Yeah, those simulations looked at $+ in various initial vibrational states, colliding with Rb. One key finding was that the cross-section for vibrational quenching, going from vital to a lower state variable, was actually quite similar for different starting variable values, at least for the lower states studied.
So the initial vibration didn't matter too much for the chance of quenching.
It seemed less sensitive than one might initially guess. Furthermore, the total cross-section for any inelastic or reactive process was found to be very close to the prediction from the simple Langevin capture model, especially at low collision energies.
Ah, so capture seems to be the bottleneck. Once they're caught, something interesting happens.
That seems to be the implication, yes. The long-range ion-atom attraction really governs the initial probability of interaction. They also looked at dissociation breaking the Barber plus bond. As you'd expect, this only happened when the collision energy was high enough to overcome the ion's binding energy, and the probability increased with collision energy.
It's fascinating how even in these relatively complex molecular ion-atom collisions, those fundamental long-range forces still play such a crucial, often dominant role in determining the overall reaction rates. Okay, wrapping up, let's touch on the really big picture. Ultra-cold physics and the quest for new physics. How do these incredibly cold controlled systems help us probe the very boundaries of our understanding of the universe?
Ultracold systems offer an absolutely unparalleled platform for high-precision measurements. That's really the key.
Why are they so good for precision?
Several reasons. By cooling atoms and molecules down to microkelvin or nanokelvin temperatures, we drastically reduce their thermal motion. This massively suppresses the Doppler broadening of their spectral lines, the smearing out of frequencies due to motion towards or away from the detector.
So sharper signals.
Much, much sharper. Also, the experiments are typically done in ultra-high vacuum with very low densities, which minimizes pressure broadening shifts and broadening caused by collisions. Plus, the long observation times possible with trapped particles further increase the potential precision. You get incredibly narrow spectroscopic features to measure.
And what kind of fundamental questions can we hope to answer with this extreme precision? What's the payoff?
One major ongoing effort is the search for possible time variation of fundamental constants.
Like constants not being.
Constant.
Exactly. Are the values we measure today for things like the fine structure constant alpha, which governs electromagnetic interactions, or the proton-to-electron mass ratio, PM, exactly the same as they were billions of years ago? Or are they slowly drifting over cosmological time? How can ultra-cold molecules help answer that?
Certain molecular transitions, especially vibrational transitions in molecules with specific structures, can be extraordinarily sensitive to tiny changes in these constants. If alpha or weak were different in the past, the frequencies of these transitions would also be slightly different. By comparing ultra-precise lab measurements today with astrophysical observations of molecules in distant and therefore ancient gas clouds, or by just monitoring lab frequencies over several years, we can set incredibly tight limits on any possible drift. These sensitivity coefficients, Taylor-Joller, quantify exactly how much a given transition frequency would shift if a fundamental constant changed.
So we're using ultra-cold molecules as exquisitely sensitive clocks or rulers to see if the very rules of the universe might be changing, even imperceptibly slowly. That's amazing. Your sources also mention a connection between ultra-cold molecules and the search for extra dimensions. How on earth could that possibly work? Seems like a leap.
It does sound like sci-fi, but there's a potential link through gravity, actually. Some theories beyond our current standard model of particle physics, like certain string theories or models like the ADD model, or Arkhanihame-Dimopoulos-Tavali, propose the existence of extraspatial dimensions beyond the three we experience. These extra dimensions would likely be curled up or compactified on a very small scale.
Okay, tiny hidden dimensions.
Well, these theories often predict that gravity, unlike the other forces, might be able to propagate into these extra dimensions. If that's the case, it could lead to deviations from Newton's inverse square law of gravity, specifically at short distances comparable to the size of these extra dimensions.
Gravity might be different up close.
Potentially, yes. It might become stronger than expected. Now, how do you measure gravity at micron or submicron scales? It's incredibly difficult because gravity is so weak compared to electromagnetic forces. But ultra-precise measurements of the forces between neutral molecules at very short separations in ultra-cold systems could potentially search for these deviations. If there's an extra gravitational-like force showing up at short range due to extra dimensions, it might be detectable as a tiny modification to the expected van der Waals or Casimir forces in these exquisitely sensitive experiments.
So by measuring the forces between ultra-cold molecules with incredible precision, we might indirectly see the influence of hidden dimensions leaking out through gravity.
That's the hope, or at least one speculative but exciting possibility. It's pushing the limits of precision measurement to look for tiny cracks in our current understanding of fundamental forces in space-time.
It's just mind-blowing to think that experiments happening with lasers and vacuum chambers on a tabletop, manipulating atoms and molecules at near absolute zero, could potentially have implications for the fundamental structure of space-time itself, or tell us that the laws of physics are constant.
Absolutely. The level of control and the sheer precision we can achieve in ultra-cold science opens up these unique windows into some of the deepest questions in physics, questions that were once considered purely in the realm of theoretical speculation or cosmology.
Well, this has been an absolutely incredible deep dive into the truly weird and wonderful world of cold and ultra-cold chemistry and physics. We've journeyed from the fundamental forces like van der Waals, defined what ultra-cold even means, looked at how particles scatter, the power of Feshbach resonances,
Explored exotic states like BECs, the role of dipoles, the amazing techniques used for cooling and trapping,
delved into complex molecular collisions, three-body physics like Efimov states, giant Rydberg atoms, hybrid atom-ion systems.
and even saw how these systems are used to study cold chemical reactions and push the frontiers in the search for new physics beyond the standard model.
It really makes you marvel at how manipulating matter at these extreme conditions, this ultimate level of cold, allows us to explore the fundamental laws of nature in such profound and, frankly, unexpected ways.
It really does. And it leaves you wondering, what are the ultimate limits of control we can achieve over these quantum systems? What completely new quantum phenomena or states of matter are still waiting to be discovered down there in the nano-Kelvin regime?
Yeah, and what new technologies might eventually emerge from this fundamental understanding? Quantum sensors, maybe even new routes for quantum computing.
Precisely. And what unexpected discoveries about the universe itself await us as we continue to push these boundaries of precision and control in ultra-cold science? It feels like there's still so much territory to explore.
Fantastic food for thought indeed. A huge thank you for guiding us through this intricate landscape. And thank you for joining us on this deep dive into the fascinating world of ultra-cold science. Until our next exploration.